So hi everyone. In the last video, we have discussed about demand paging. And assuming that eCPU tries to access a page, let's say this page 2 of process 2 that is not loaded into the main memory, as you can see the bit is invalid, then a page fault happens. So what the CPU does, what happens is the control is transferred into the OS to request the desired na process from the secondary memory, load it into the main memory, and then update the page table and restart the instructions. So what happens if there will be plenty of page faults? So it is actually expensive and the process spends most of the time paging in and out instead of executing code. So this is the formula for computing the performance of demand paging. The page fault rate can range between 0 to 1. So if P is equal to 0, that means that there is no page fault, or every time a CPU tries to access a certain page, it is always loaded in the main memory. Okay, but if P is equal to 1, then every reference is a fault. Now, this is how we compute the effective access time, or EAT. So EAT is equal to 1 minus P, or the page fault rate, times the memory access time, plus the second term is P times all the time that we have to spend for paging in and out. So that would be page fault na overhead plus the swap page out plus the swap page in plus the restart na overhead. Okay, because if we have to go back here into our process again, we have to, OS has to request for the desired page, then page it in, and then update the page table, and then restart the instruction again. So yeah, so all those time that we have to spend on those extra na process is also considered here. Okay, so what happens if P is equal to 0, or page fault rate P is equal to 0? That means that there is no page fault. So if we substitute that into the equation, that would be 1 minus 0 times the memory access plus 0 times um, 0 times page fault overhead plus swap page out, swap page in, and then restart overhead. So you can immediately see that this second term will be immediately eliminated. Okay, and we will be left with 1 minus 0 times the memory access, and that leaves to 1 times memory access. So if there are no page faults, so we only consider the memory access, or the effective access time is just the memory access time. And if P is equal to 1, that means that every reference that we did is a page fault. Okay, and if we substitute that into the equation, that would be 1 minus 1 times memory access plus 1 times all these terms. Okay, so what happens is we are not able to get the memory access since it is not in the main memory. So that would be 0, right? And the effective access time will be 1 times the page fault overhead plus swap page out, swap page in, plus restart overhead. But of course, note that the page fault rate can range between 0 to 1, not just 0 or 1 values. Okay, so let's have an example. Assuming that we have a memory access time of 200 nanoseconds and the average page fault service time is 8 milliseconds. So the average na page fault na service time already constitute all of this. The page fault overhead, swap page out, swap page in, and the restart na overhead. Okay, so we assume all these values. So as you can see that compared to the memory access time, the page fault service time is much, much larger. So we had our formula earlier, which is 1 minus P times the memory access time plus P times the average page fault service. So if we substitute that into our equation, that would be 1 minus P times 200 plus P times 8 milliseconds. And if we just uh, simplify it further, this would be 200 minus 200P plus 8 million P, right? So and then if we further simplify this negative 200p plus 8 million p will become 7,999,800. So we have then the effective na access time equals 200 plus 7,999,800 p nanoseconds. Now, if one access out of 1,000 causes a page fault, so we said earlier, right, that the page fault rate is between 0 to 1. And in this case, this is the rate, 1 out of 1,000. So if we just compute the page fault rate, we simply divide 1 over 1,000, and that would give us P equals 0.001. Okay, so the effective access time then, which is equal this 200 plus around 7 million P. So we simply have to substitute the P equals 0.001 here. And we will have 200 plus 7,999.8. And it is equivalent to 8,199.8 nanoseconds, or about 8.2 microseconds. So this is a slowdown by a factor of over 40. So how did we compute that? So our memory access time without the page fault, if let's say this is 0, so this is 0. So this would be only 200, right? 200 millisecond. Our effective na access time will only be 200 millisecond if we don't have any page fault. Okay. And if we have a page fault, considering that if one access of 1,000 causes a page fault, our effective na access time will be 8.2 microseconds. And as you can see, it has slowed down by a factor of over 40. Okay, now, in the next video, we are going to discuss page replacement.